Hello, my name is Uma Rajagopalan, and today's video is about using Newton's second law and the basic energy principles to track and analyze the motion of a spring mass system. The objective of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. This motion contains some of the behaviors that can be seen in this extreme rope sports example. It should be noted that the calibration length, time between video frames, and relevant masses are the same as those in the video. These are the equations and concepts that will be needed and incorporated throughout the analysis. In this model, we were given and calculated some of the initial conditions. The mass of the object at the end of the spring was given to be 0.402 kilograms, and the initial velocity of the spring mass system is 0, since the system starts at rest. Based on the tracker data, it was determined that the initial position of the system was at negative 0.104, negative 0.6440 meters. Based on the graph given in the video with movement only in the vertical direction, the average period for an oscillation was determined to be 1.524 seconds. Using this value for the period and the equation relating the spring constant and the period, the spring constant K was determined to be 6.83. Finally, the initial length of the unstretched spring, L0, was determined to be 0.123 meters. To create a computational model of this problem, modifications had to be made to the Python code that was given to us. The basic energy principles that will be used are the kinetic energy, gravitational potential energy, and the elastic potential energy. The change in energies for these are calculated and combined to calculate the total energy of the system. The net force was calculated by combining the force of gravity and the force of the spring, and this net force was implemented into the velocity for the object. To compare the computational model predictions to the actual data, the tracker data was implemented into the Python code, and as can be seen, the red ball is the tracker data and the blue ball is the Python code. As you can see, there is a slight lag in time between the kinetic energy graphs for the two balls. This can be accounted for because the tracker data takes into account other forces that are not accounted for in the code, such as air resistance, which could have slowed the mass spring system down at certain times. The first "what does it mean" question is, for your model, is the energy principle satisfied? The energy principle is satisfied in the model based on the graphs produced. This is because delta E, or the total energy of the system, is 0, and each energy type is cancelled out as seen in the graph above. The second "what does it mean" question is comparing the estimated oscillation periods between the x position data and the y position data from tracker, and what accounts for these differences. When looking at the tracker data, it was determined that the oscillation period for the x direction was 1.61 seconds, and the oscillation period for the y direction was 1.52 seconds. However, neither of these values was used in the Python code because the spring mass system is not only moving in one direction. It has both an x and y component, so neither of these oscillation periods is sufficient in explaining the system's movement.